Prof. Anirudh left the meeting.
Start the screen.
Yeah,
Okay. Yeah. Hello, everyone. Welcome to today's live session for NPTEL Linear Algebra course. My name is Kishore, and I have with me Anirudh, Sreekar, and Prafull. We are the TS for this course, and we are going to be conducting today's session. So in today's session, we are going to be talking about the important concepts of weeks 5 to 8 as a continuation of what we did last week in weeks 1 to 4. So if you have any questions about this week's concepts, weeks 5 to 8, about the assignment questions, about last week's concepts, really anything about this course at all, please feel free to write them in the chat window. We'll be looking at the questions over there. Okay, so let's get started. Sreekar.
Yeah, I hope it's visible now.
Yes, it is. All right. So first question. Okay, so the main concepts in assignment 5 included eigenvalues, eigenvectors, and their properties. So we've selected 2 questions from assignment 5, which we think encompasses all of these properties together in just these 2 questions alone. So let's start with question 10. I'll read the question out. A, we've given it as, we've given the coefficient, the terms, elements of the matrix A, B, C, D is the matrix representation of a linear map T. And T has the following eigenvalues and the corresponding eigenvectors. So lambda 1 is 3, V1 is 1, 3. And the second eigenvalue, lambda 2 is 2, and the corresponding eigenvector is 2, 4. And we've been asked to find some linear combination of the elements of the A matrix. Next. Okay, so we see that we've been given the eigenvalues and the eigenvectors. The first thing that should come to our mind when we see this is the diagonal form of this linear map. So we know that in the eigenvector basis, the matrix representation of this map T is diagonal, and the diagonal matrix, that is the matrix in this diagonal in the eigenvector basis, is given by B. That is, we've just taken the eigenvalues and put it along the diagonals. So the first column is 3, 0. We have a diagonal matrix, so the diagonal elements are 3 and 2. And separately, let us also just keep aside our conversion matrix, our change of basis matrix from the eigenvector basis to the standard basis. So this is just a continuation of what we were discussing last week. We know that any non-standard basis to standard basis, you take the eigenvectors, the vectors of the basis, and you put it as the columns. So the first vector is 1, 3, put it as the first column. Second vector is 2, 4, put it as the second column. Next. Okay, so we have all of our tools to solve the question, and now let's get going and solving it. So the aim is to write a replacement for the matrix A. So we know that A takes the input in the standard basis and the output in the standard basis. Could you go back to the previous slide? I forgot to mention that the basis everywhere is the standard basis. I've written it in brackets in the question. What that means is that the vector representations of V1 and V2 are in the standard basis. A is in the input and the output of A is in the standard basis, and so on. Everywhere it's standard basis. Next. So A takes the input in the standard basis, and A spits out the output also in the standard basis. But we know that B is in the eigenvector basis. So we need to convert our input from the standard basis to the eigenvector basis. So the first thing we need to do is convert. So we apply S inverse. We know that S takes us from the eigenvector basis to the standard basis. So S inverse should take us from the standard basis to the eigenvector basis. And now that B times, let's say the vector in the standard basis is V. So B times V, sorry, S inverse times V. S inverse times V will be in the eigenvector basis. So now we can apply B. And finally, the output, we want to convert it back to standard basis. So we apply S. So A is equal to S, B, S inverse. And you can just simply multiply these 3 matrices, S, B, S inverse, and you can get it as 0, 1, minus 6, 5. And if you go back to the previous slide, they had asked for A plus 2B minus C plus D. You just calculate that and you can get it as 13. Quite an easy question. So two of the main things that we should wonder in this question is, the first one is, I had immediately said we can write A in the diagonal form with the eigenvalues along the diagonal. So we know that we can't always diagonalize a matrix, right? Why were we immediately able to say that we could find a diagonal form for this linear map? The reason is that we have enough eigenvectors as the dimension of this. So A is a 2 cross 2 matrix, and we have already been given two linearly independent eigenvectors. And we know that if we have, for an n cross n matrix, if we have n linearly independent eigenvectors, we can always find a diagonal form. So just to reiterate, when is a matrix not diagonalizable? If we cannot, we won't always have n linearly independent linearly independent eigenvectors. So we won't always be able to diagonalize it. But in the question itself, we've been given two linearly independent eigenvectors. So we can automatically say that there will be a diagonal form. And the next thing to notice is that when I said that we have the change of basis matrix, I wrote it as 1, 3, 2, 4. I didn't put the 2, 4 as the first column and 1, 3 is the second column. So why did I do that? Why can't what is wrong with putting it the other way? And the answer is that in the matrix B, we put 3 as the first diagonal element and 2 as the second diagonal element. So the eigenvector corresponding to the eigenvalue 3 has to come in the first column, and the eigenvector corresponding to eigenvalue 2 has to come in the second column. So that was, if you try it the other way, you will notice that it won't become diagonal. If you multiply SB, S inverse using the vectors in the other form, it won't multiply and give you A. So those are the two key things in this question. So now let's move on to the next question. All right. So another key concept in week 5 was invariant subspaces. So we think that question 12 encompasses this really well. Let's remind ourselves of the definition of an invariant subspace. So a subspace U, which is a subset of V, is said to be invariant under T if TU belongs to U for all U, meaning U is also part of U and TU is also part of U. It's not necessary that for any, like if you have a subspace V and you take a subspace W and you take a vector in W and you apply T to it, it's not necessary that resulting vector has to stay inside W. But if it does, then it's called an invariant subspace. Okay, so here's the question. Let the matrix representation of the linear operator T from V to V under this given basis V1, V2, V3, V4 in this specific order be this matrix here A. And all of the A's we mentioned 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, 4, 3, 4, 4. These are all non-zero. And we've been given 4 options. We've been asked which of the following are true. So we'll be solving just the first option because the second and third the method to solve it are exactly the same. Let's let's go in depth into the solving of the first option. Next. All right. So the question, could you go back to the previous slide? The question, what we're trying to check is if span of V1, V2 is an invariant subspace under V or not. So this is the procedure we're going to be showing is more or less a standard procedure to check if a certain span is an invariant subspace. Next slide. Okay, so we know that any vector in this span can be written as a linear combination of the elements of the span. So V is equal to V1 times V1 plus V2 times V2. And in the given vector, the given basis for A is V1, V2, V3, V4. So if we express our vector V in terms of this basis, we simply have the coefficients B1, B2, 0, 0. All right, so now we have our input in the given basis BV. So now we can apply A. And we do A times V. So we just multiply the two matrices out here. I put A and put V next to it. And you multiply it out, we see that we get A11B1 plus A12B2 plus A21B1. The second term is A21B1 and A22B2. And let's convert now back from this in this basis form to the regular form. So in terms of V1 and V2, So it just becomes A11B1 plus A12B2 times V1 plus A21B1 plus A22B2 times V2. And obviously, this is a linear combination of V1 and V2, so it belongs to span of V1, V2. And So we are input vector from span of V and V2. It spits out an output which is also in the same subspace span of V1, V2. And hence, by definition of invariant subspace, the span is an invariant subspace of V under T. And the options 2 and 3 are exactly the same. The option 2 dealt with the span of V3, V4. Option 3 dealt with span of V1, V2, V4. And you can follow the exact same procedure and just check that these two will also be correct. All right, next slide. So the first three options were correct. And the fourth option is asking us to check if A44 is an eigenvalue or not. So this is just quite an easy extension of the question. So let's just stick to our standard way of expanding the determinant to find the eigenvalues. So we know that the eigenvalues are given by the solutions to determinant of A minus lambda I equal to 0. So we just we subtract lambda along the diagonals and we try to find the determinant. And really, most of the questions involving checking if an eigenvalue, if a certain number is an eigenvalue and so on, just involves a clever expansion of this determinant. So here it's quite easy to see. The most natural thing to do is to expand along the last column. So let's expand this determinant along the last column. We get A44 minus lambda times the 3 cross 3 determinant over there. So now we don't care about what is inside the 3 cross 3 determinant. I just put it as 3 dots over there. All we care is that if we set lambda is equal to A44, this determinant is going to go to 0. And so automatically we can say that since A minus A44I, determinant of that is equal to 0, A44 has to be an eigenvalue. So quite an easy question. A44 is an eigenvalue. So for this question, all 4 options are correct. Okay, let's move on to assignment 6. So in the previous live session, there was a question in the chat box about some easy methods to find eigenvalues. And that is why we have chosen this particular question. So you can see we have a fairly complicated matrix with some fairly large numbers, 1, 1, 2, minus 34, and so on. We've been asked to find the eigenvalues of this. And the hint is that we don't need to do it using a direct computation. By direct computation, we mean by expanding, we take A minus lambda I and then try to solve a characteristic polynomial by expanding the determinant and so on. We instead have to use the properties of the eigenvalues and try to find this. Right, next. So anytime we have these kinds of questions, at least from an exam point of view, there is always a standard method to solve this. So the first property that we use is that the sum of the eigenvalues is a trace, which is the sum of the diagonal elements. In this case, 112 plus 51 minus 14. And the second property is that the product of the eigenvalues is the determinant of this matrix. Any additional conditions have to be found by clever methods. And what I mean by that is there is no standard way of finding it. The condition will be specific to this matrix. So specific to A, we have to try and perform some jugglery and find some additional constraint to relate any two eigenvalues and so on. In fact, for this 3 cross 3 matrix, you only have to find one condition. For a 4 cross 4 matrix, you'll have to find 2 conditions. For 5 cross 5, 3 extra conditions, and so on. Okay, anyways, let's solve this question. Next. Okay, so the first step, the 3 things we said were that trace, determinant, and the special condition. So the first thing let's do is the determinant. Previous slide. So we can see that the first, just by some observation, just by staring at this question for a little while, you can see that the first 2 rows are multiples of each other. The second row is minus 1.5 times the first row. You can easily see it from 39, 26, and 51, 34. 168, 112 also, you can just quickly confirm it using a calculation. So we know by the properties of determinants that if any 2 rows are multiples of each other, then the determinant will automatically go to 0. So the determinant is 0, which means that lambda 1 times lambda 2 times lambda 3 is equal to 0. So at least one of lambda 1, lambda 2, or lambda 3 have to be 0. So 0 is an eigenvalue. So out of the 3, we have now found 1. All right, and typically in the three things that we do, just determinant, trace, and the special condition, we always leave trace to the last because that's like the final thing. We try to do the special condition first, second. So now this special condition is not very trivial. You'll have to stare at the question for a while, and it may strike you, it may not strike you. But anyway, since this is an assignment question, you must have had a significant amount of time to look at this question yourself and try it out. So here is an elegant way of doing it. The sum of each column results in -1. The previous slide. So you can just see for yourself. You just can try with the second and third row first. They're easier to compute mentally. So the last row, you can easily see that the sum of the columns, that is minus 26 plus 39 minus 14 is minus 1. And similarly with the second and the first columns as well. So if we take A transpose and we multiply by 1, 1, 1, then we get minus 1, minus 1, minus 1, which means that minus 1 is an eigenvalue of A transpose. Eigenvalue of A transpose. And we have to now use the additional property that any eigenvalue of A transpose is also an eigenvalue of A. So by using this property, since minus 1 is an eigenvalue of A transpose, it will also be an eigenvalue of A. So we have our second eigenvalue, minus 1. And finally, we use a trace condition, 0 plus minus 1 plus our third eigenvalue, lambda 3, is equal to the sum of the diagonal elements, 112 plus 51 minus 14. And you can simply just move the minus 1 to the other side, and lambda 3 is equal to 150. So the eigenvalues are 0, minus 1, and 150. So in this somewhat, it's not a simple case, but it is a 3 by 3 case. And often you will have to encounter much, much larger matrices. You can think of things like page rank and so on, in which you can't keep coming up with these clever methods to find eigenvalues like this. For the sake of the exam, you will have this all we can do. But in real life, we need to find a more standard way of finding the eigenvalues. And that is when we resort to numerical linear algebra. So we don't actually find the eigenvalues exactly. We find an approximation to these eigenvalues by some standard numerical linear algebra techniques. And that is what is used in real life to find eigenvalues of matrices. And sir would have mentioned during the lectures that, in fact, to find the roots of a polynomial also, we using these numerical techniques to find eigenvalues is the standard way. So in this, we actually went the other way around. To find the eigenvalues, we expand the determinant and we try to solve the characteristic polynomial. Instead, in real life, to solve the polynomial, we solve for eigenvalues. It's the other way around. Anyway, that's just a bit of information. Nice, something nice to know. So let's go to the next question. Okay. So this question deals with the properties of eigenvalues. This uses pretty much all the properties that almost all, several of the properties that sir would have mentioned during the lecture. So let's look at the question. We have a matrix A, and we've been given that the eigenvalues are minus half, 1 by 4, and 1. And we're given a matrix B in terms of matrix A. So A inverse minus 3i, the whole transpose, plus 5i. And the eigenvalues of this are PQR, with we've been given a condition mod P less than mod Q less than mod R. Anyway, for this question, it doesn't really matter. We've been asked to find the three eigenvalues, P, Q, and R. And we've been given one extra question. Is the resulting matrix B in terms of A, is it invertible or not? Okay, so let's start. So we've been, in the question itself involves A inverse. So lambda, we can assume, we've already been given the eigenvalues A. Anyway, they're all not going to be 0. So let the lambda not equal to 0 be an eigenvalue of A. So the first property we use is that if lambda is an eigenvalue of A, 1 by lambda is an eigenvalue of A inverse. So A inverse will have the eigenvalues as 1 by lambda. So minus 2, 4, and 1. And then 1 by lambda minus 3 will be an eigenvalue of A inverse minus 3i. So this is the second one. I'm not sure if sir did this during the lectures, but this is quite easy to check. If you subtract any k times and the identity matrix from a given matrix, then the eigenvalues will also get subtracted by k accordingly. In this case, it's subtract by 3i. So the resulting eigenvalues of this A inverse minus 3i is going to be 1 by lambda minus 3. And the next property we use is that transpose, the eigenvalues remain the same. So A inverse minus 3i, the whole transpose will still have the same eigenvalues, 1 by lambda minus 3. And then we use the adding subtracting of an identity matrix again. So we add 5 times I, and so the eigenvalues will also get added by a 5. So 1 by lambda minus 3 plus 5. That's 1 by lambda plus 2. These are eigenvalues of A inverse minus 3i, the whole transpose plus 5i. This is equal to B. Notice that we didn't put any condition on this lambda. So this should be applicable to all the 3 lambda of A. That is minus half, 1 by 4, and 1. So you simply put 1 by lambda plus 2 is equal to minus half and find the lambda for that. 1 by lambda plus 2 is equal to 1 by 4, find the lambda for that. And for the third one also. And we can see that the eigenvalues of B are 0, 6, and 3. So we have the first part of our question, P, Q, and R, 0, 3, 6. And the second part of the question is the matrix B invertible. One of the eigenvalues is 0, so B is not invertible. Next slide.
Actually, just a small correction. Actually, you said the other way around. So you have to substitute lambda equal to minus 1/2, 1/4. Right?
Okay. Sorry. Yeah, correct. 1 by minus half plus 2. Right. Sorry. Okay. So in two places in the previous slide, we mentioned that if 0 is an eigenvalue, then the operator is not invertible. So this might seem obvious to many, but there are also many who may not see this immediately. So I just thought we'd go over it again. So here is the small piece of logic, quite easy to see that if 0 is an eigenvalue, then the operator is not invertible. Okay, so let's start from the left end and go towards the right end. So operator A, let's assume it's not invertible. Then since it's an operator, if it's not invertible, it cannot be injective. We said in the slides that it not injective, not surjective, not invertible, they're all equivalent statements in the case of an operator. So we can immediately say that if A is not invertible, since it's an operator, it should not be injective. And using the property of injectivity, it should have a non-zero null space. So AV is equal to 0 for some non-zero V. And we can write 0 as lambda times V, where lambda is equal to 0. So AV equal to lambda V, where lambda is equal to 0. This is obviously an 0 will automatically form an eigenvalue. You can go the other way around also. 0 is an eigenvalue. So I can AV is equal to lambda V, where lambda is equal to 0. You can just go in the other direction. You can show that A is not invertible if 0 is an eigenvalue. So this is something nice to remember. Anytime you see an eigenvalue to be 0, it is not invertible. All right, we used a bunch of properties in the previous slides related to eigenvalues, and it's a good idea to summarize all of this. So if lambda is an eigenvalue of A, the first thing we said is that if the inverse exists, inverse, then the eigenvalues are going to be 1 by lambda. And the second property we use is that if we add some multiple of the identity matrix, some k times I to the matrix A, and the eigenvalues of the original matrix A will also get added by k. The third property we use is that A and A transpose have the same eigenvalues with the same multiplicities. This is not very hard to see, because to find the eigenvalues of A, we have a determinant of A minus lambda I equal to 0. Find the eigenvalues of A transpose, it will be determinant of A transpose minus lambda I equal to 0. And these determinants, we know that by the properties of determinants that determinant of a matrix is also equal to the determinant of its transpose. So just by writing out the determinant, you can usually see that the eigenvalues must be the same, since the characteristic polynomial is the same. And the multiplicities, the arithmetic and geometric, will also automatically come out to be the same. And finally, the property we discussed in this slide, if A is non-invertible, if it has, that's if and only if, at least one eigenvalue is 0. So in both directions, A is non-invertible if it has an eigenvalue 0, one or more. And if A has or if at least one of the eigenvalues is 0, A is not invertible. Next. Okay, so I think this is the last question for assignment 6. So let's look at a crucial application of the linear algebra that we have discussed in the first 6 weeks, which is the linear state space system. So we have any vector xk, and we apply A to it, we get our xk plus 1. A is an operator. And we have been given this A, 0.2, 0.8, 0.8, 0.2. And we've also been given x0. And we keep on applying A to the x. So we get A times x0 is x1, A times x1 is x2, A times x2 is x3, and so on. We keep on repeating the same thing. And we want to know what happens to xk as k tends to infinity. We've been given 4 options, and we've been asked to find which one is correct. Okay, next. Okay, so once again, regarding these linear state space system style questions, we have more or less a standard procedure. So the first thing we have to do is to assemble the tools necessary for this question, and that for this type of question is to find the eigenvalues and eigenvectors. So we just have a 2 cross 2 matrix. We just have to find the trace and the determinant, and you can easily find the eigenvalues as 1 and minus 0.6, and the corresponding eigenvectors are 1, 1, and 1 minus 1. And now next thing to do is we've been given that x0 is equal to 1, 0, and we have to try and express it as a linear combination of v1 and v2. So this one is quite easy. 1, 0 is half of 1, 1 plus half of 1 minus 1. And now we just do a times x0. Let's first do a times x0 and then we'll look at a power k times x0. So a times x0 is going to be a of half times 1, 1 plus half times 1 minus 1. And since both of these are eigenvectors, so a times 1, 1 is going to be just 1 times 1, 1. And a times 1 minus 1 is going to be equal to minus 0.6 times 1 minus 1. So if we do this, and that's how we get x1, we again apply a to x1. We do the same thing over and over and over. And we finally get a raised to k times x naught, and that will be equal to xk. And we can see that the half terms will stay as it is. The 1, 1, 1 minus 1 stays as it is. The only thing that keeps getting multiplied is the eigenvalues 1 and minus 0.6. So we get half 1 raised to k by 2, 1 times 1 times 1 times 1 k times by 2 times 1, 1 plus minus 0.6 raised to k by 2 times 1 minus 1. And now this is xk. So we have xk. Now all we have to do is set k to infinity. So we can see easily that you multiply anything less than 1 infinite times, it will just keep on shrinking to 0, right? Minus 0.6 times minus 0.6 will be 0.36. And then you multiply another 0.6, that will become smaller and smaller and smaller. As you multiply more and more, just goes to 0. 1 raised to k stays as it is. Nothing happens to that. So as k tends to infinity, the second term simply vanishes, and we are left with 1 raised to k by 2 times 1, 1, which is just half times 1, 1 is 0.5, 0.5. And that's it. That's all we have our answer. So this also represents a fairly simple application of all the things we have learned so far. And that covers it with the assignments 5 and 6. We'll be moving on to 7 now. So I'll give it over to my fellow TA, Anirudh, to discuss those. Thanks.
Yeah, I'll be discussing 3 questions from assignment 7. The first one is actually based on properties of inner product. We are actually doing the question 2 from assignment 7, where we are given 2 vectors, v1 and v2. We are given the norms of these vectors, and we are also given the inner product of these 2 vectors. We are asked to find the inner product of these new vectors, v1 plus 3v2 and v1 plus minus 2jv2. Here, by the way, j is nothing but root of minus 1. In electrical, we usually use j instead of I, because I is used for current. So we are given 4 options. We need to find this inner product. Next. So as you may have expected, we just use the properties of inner product to approach this question. Next. So a recap, the properties which will be useful here are that inner product is actually additive in both first and second arguments. That is an important property we'll use. And the conjugate symmetry, as well as these 2 properties, where if you have lambda v in the second argument, it will be the same as lambda bar times the inner product of u and v. And if you have lambda u times lambda u comma v, then you have lambda times u comma v. So we'll make use of these 4 properties to arrive at the answer. Next. So initially, in the first step, we make use of additivity in the first argument. So we will write it as v1 comma the second vector plus the 3v2 comma the second vector again. And then we use the additivity in the second argument, which will give us 4 terms. The first term will be the norm of v1. The last term will involve a multiple times norm of v2. And the second and third terms will involve v1 comma v2 and v2 comma v2. An important part is that in the second term, we have written plus 2j. That is because we had minus 2j in the second term of the inner product, which means we need to use the third property. So we'll end up with 2j outside. So yeah, that's about it. We just need to substitute the values from given in the question, and we also need to make sure that we also need to make use of the property that v2 comma v1 is v1 comma v2 bar. So making use of that, we get 3 minus 4j here, and substituting, we end up getting 10 plus 48j. That will be the answer. It's a pretty simple question. Next, we talk about orthogonal complements, which is question 7 from assignment 7. We are given a subspace U, which is a span of 2 vectors. These 2 vectors are obviously linearly independent. So these 2 vectors are actually the one of the bases of the subspace U, and we are inside vector space R4. And we need to find an orthonormal basis for U. which is basically all vectors in R4 which are orthogonal to all vectors in U. Or in other words, we need to find all vectors in R4 which are orthogonal to both these basis vectors we have seen above. So we are given 4 options, and let's see how we do it. Next. So the standard method for solving such questions would be to basically take the basis of U, and then we expand it into a spanning set for R4 by basically adding a basis for R4. For example, if you have basis of U as 1, 2, 3, 8 and 1, 3, 4, 11, we could add the we could just add the standard basis of R4 to form a spanning set for R4, and then we could perform the Gaussian elimination to get a basis of R4, and then we perform the Gram-Schmidt orthonormalization to get an orthonormal basis for R4. An important property that we make use of here is that during Gaussian elimination, if we order let's say n vectors in a matrix one below another, there is the property is that the span of any first I vectors will remain the same before and after Gaussian elimination. I'll reiterate, like if you have a Gaussian elimination where there are n rows, the span of first I rows before and after Gaussian elimination will remain the same. We make use of this property here. That is the reason this method actually works. And the same property also holds good for orthonormalization, where before and after orthonormalization, the first I vectors, the span of the first I vectors remains the same. So after orthonormalization, we'll be left with 4 vectors, in which the first 2 vectors will again be a basis for orthonormal basis for U, and the remaining 2 vectors will be the orthonormal basis for U per. As I told, the order of the vectors should not be changed, because we are making use of the fact that span of first I rows or the first I vectors while performing orthonormalization or Gaussian elimination remains the same. That is a crucial property we are using here. Next, but we don't need to actually use this. As we saw, the inner product defined here was dot product. So all we need to do is basically we could just stack the basis vectors of U into a matrix called A, and then we just, as I said, we just need to find all vectors in R4 which are orthogonal to all vectors in U, which means basically we need to find all vectors in R4 which are orthogonal to both the basis vectors of U. So as inner product is basically dot product here, we just need to find the null space here of this matrix A. That is what we do. We perform Gaussian elimination on A. We end up getting this triangularized form, and the last 2 variables will be the free variables, and the first 2 will be the dependent variables. The standard method, we find the null space as span of -1, -1, 1, 0, and -2, -3, 0, 1. And these 2 form a basis of the null space. The null space is nothing but U perp here. So we just then orthonormalize this basis to get an orthonormal basis for U perp. This is the standard Gram-Schmidt orthonormalization that we use to get this basis B. But we should note that the subspace U can have many bases, and as it has many bases, it can also have many orthonormal bases. So we need to check that the other options given in the question are not orthonormal basis of U perp. So the standard way we could do this is basically if the other options are actually basis for orthonormal basis for U, then A times those vectors will definitely should give 0 vector. We can check that, and we should also check for orthonormality of those vectors. We could check whether they have norm 1. We could also check whether the 2 vectors given in the other options are actually orthogonal to each other. We check these 3 properties: orthogonality and norm 1, and whether they belong to null space of A, then we would have checked the other options as well. It turns out that in this case, only option B will be correct. Okay, now moving on to the next question. We have assignment 7, question 9. This is basically a question purely based on properties of norm. So we are asked which of the following are not valid norms. Invalid norms, we are supposed to find invalid norms, are given the 4 options. So let's go next. Let's go over the conditions for norm, or basically the definition of what constitutes a norm. We have positivity, where every vector, a norm defined on a particular vector space capital V, should satisfy all these 4 properties. Any vector v in the vector space v should have a norm greater than or equal to 0, and we should also have definiteness, as you know. Norm of v is 0 if and only if v equals 0. And similarly, as we discussed in the lectures, as Sir discussed in the lectures, we also need to the norm definition of the norms to also satisfy absolute scalability and triangular equivalence. So we'll make use of the definition of this conditions for norm or the definition of norm to find out which are the invalid norms. Next. So in the first option, actually we had norm of x1, x2, x3 as mod of x1 plus x2 plus x3. So if we take a vector such as 1, minus 1, 0, which is a non-zero vector, we end up getting a 0 norm, which means the definiteness is not valid here, which is not satisfied by this definition of norm. So this is not actually a valid norm. Mod of x1 plus x2 plus x3 is not a valid norm. The second one is basically the sum of the absolute values. That is basically sum of mod x1 mod x8, which is basically the one norm as defined in class, which is a valid norm. The third option, we actually have a mod of x1 cube plus mod of x2 cube plus mod of x3 cube. We need to again, here we see that the norm of 100 is 1, but we see that norm of 200 is nothing but 2 times 100 is 8. So absolute scalability is not valid here. It's not satisfied here because we are multiplying by 2, and we should be able to take the mod 2 outside. Mod 2 times 1, norm of 100 should be 2, but we are getting 8. So this is not a valid norm again. We could actually use the same case for option D as well. I use a different one. x1 cube plus x2 cube plus x3 cube. Here we see that even positivity is not satisfied. At least in option C, positivity was satisfied because we did summation of mod of x1 cube. Here we are just doing summation of x1 cube, xi cube. So we end up getting norm of 0, minus 1, 0 as negative number. So this is again not a valid norm. So the general principle to find out if a norm is valid or not is to basically just go by the definition and try to look at the definition of norm in such a way that see it as if try to find out which conditions would not be satisfied. For example, if you have mod x1 cube plus x2 cube plus x3 cube, we see that the definition itself involves a cubic term, which means obviously the scalability won't work out because scalability requires you to take a lambda scalar outside, which requires linearity. Here we're using cubic definition. So same thing applies for D. And for option A, again, we are using mod of the sum, which again means you could find out, have a non-zero vector giving a sum of 0. So we should actually be able to find out these exceptions or these conditions not being satisfied. So next up, I'll have my colleague Sreekar explaining assignment.
Yeah. Okay. Yeah, we'll soon get over the question. So we just have 3 more questions left. So yeah, so this is a question from assignment 8, question 3. So basically, what we have here, we have a subspace U defined over here. And we need to find the projection operator onto the subspace. So the matrix of the projection operator is what we need. We also need the projection of a certain vector onto U, which is simply PU times V. Now, let's recall what a projection operator, the matrix of a projection operator can be represented by. So if you are able to find an orthonormal basis for U, it means that you can easily find the projection operator, the matrix representation of the projection operator as E1 E1 transpose plus E2 E2 transpose and so on, where EI is the orthonormal basis for U. So in this question, the only thing we have to do is we want to find an orthonormal basis for the vector space U. After that, everything is quite trivial. Now, how do we find an orthonormal basis for U? If you look at the vector space, the definition of the subspace, it says x plus y plus z equals 0. So this essentially means that x comma y comma z in a product with 1 comma 1 comma 1 equals 0. Like this is one way to approach this problem. There are many ways you can do it. So I'm starting out with this. So it means that the subspace U every vector is perpendicular to this vector 1, 1, 1, and this is, once this condition is satisfied, it means that it belongs to the vector space U, which means that U perp is equal to the span of this vector, span of 1, 1, 1. Now we know U perp. How do we find U? We want basically a basis for the vector space U. Now, if we recall from Anirudh's question, so we saw that we, to find the orthogonal complement of a certain space, we took the basis vectors as the span, as the row space, and then we found the null space of that certain matrix. So here our matrix would be simply a 1, 1, 1 matrix. And all we need to find here is find the null space of this matrix. And this would obviously be -1, 1, 0 and -1, 0, 1. This is a simple basis you can think of. You could have found out this basis from the beginning itself. When you see the vector space, you know that you'll realize that it is actually two-dimensional vector space, and you can find two vectors that satisfy this, and that would form a basis. So this was just a little more systematic procedure of doing the same thing. So now we only have a basis for U. We don't have an orthonormal basis, so we just orthonormalize it using Gram-Schmidt. So this is pretty easy. You just take 1 by √2 times this, and for this you do the usual procedure. You just subtract this vector with the projection that it has along this vector's space. So once you've done that, you can find the orthonormal basis for U. And once we have the orthonormal basis, it's trivial. We just say the projection operator is E1, E1 transpose, so E2, E2, E2 transpose. So now that we have a projection operator, finally the projection of the vector V, which is given to be 1, 2, 0, onto the vector space U, the projection of that onto the vector space U is simply PU times V. And it turns out to be 0, 1, comma -1. Yeah, so yeah, this was a pretty simple question. All we needed to do is find the orthonormal basis for the subspace of interest. Now, in the next question, we have a question about the least square solutions for an equation Ax minus b. We've been given the matrix A and the target vector b, and we want to find the x which satisfies Ax minus b with the minimum value. Now, the first thing that should strike you when you look at the matrix A is that it's full rank. You have the column space to be equal to R3, which means that because B belongs to R3 and the column space of A is basically R3, it means that B belongs to the range of T, or in equivalently the column space of A, which means for sure we have a solution to this equation, and we have a solution to Ax equal to b itself, which means the minimum error possible is actually equal to 0. And because it is also an operator, which represents an operator, because it is having full rank, it means that it's also invertible. So we can directly find the value of x which satisfies Ax equal to b, and that would be unique. X is a unique vector phi 2 minus 1, which satisfies the least squares, and here it satisfies it trivially where Ax equals b. Now the question also has a few options about null A and null A transpose A. So because A and A transpose A have full rank, the null of both of those are basically equal to 0, which means translates of null are basically the same as the vectors themselves, which means both these, all three of these options are correct. I have a short discussion about least squares, different cases. I will take it if we have more time. Yeah, so we'll move on to the last question. So here we have a question involving polynomials. Here, what we've been asked for is finding the distance of a polynomial x square from the subspace of linear polynomials and constants. So the thing is, x square lives in a subspace of the polynomials of second order polynomials, whereas the linear polynomials lives in a subspace of vectors which have only the form a0 plus a1x, for example. So you want to project the approach would be to project the vector x square onto the linear subspace. So yeah, so the way we define the distance of a vector v from a subspace U would be minimizing v minus u, where u belongs to any U belongs to the subspace U that we want to project it onto. So the subspace U is basically this subspace of linear polynomials. So this would be the distance from a subspace. We want to find the minimum distance of a vector, the vector x square from a vector U in the subspace. Now the one that satisfies that is actually equal to PUV, which is the projection of that vector onto the linear subspace. So this is something we had discussed in the lectures. So our approach should be clear. We just want to project the subspace x square onto the linear polynomials, and to find something onto the linear polynomials, we need to find a basis for the linear set of the subspace of linear polynomials. And once you've got the projection, we just compute the distance between x square and the projection. Now U is basically the subspace of linear polynomials. We need to find this, which is given V, PUV, as we discussed in class, would be basically the projections of V onto the basis vectors E1 and E2 once we found an orthonormal basis. Now, how do we find an orthonormal basis? That's simple. For linear polynomials 1, x, this set forms a basis, because you can express any linear polynomial in terms of these. And now we have to orthonormalize it in order to find a projection operator easily. So we have these two vectors once we've orthonormalized it. And all we have to find is V, E1 and V, E2. So those are simple. So you just take so this is the definition of our inner product. That's given the question. All we have to do is take the inner product between x square and 1 and x square and the other basis. So we find out what is the projection of these onto them. And then it's now simple. PUV is simply 1/3 plus 1/2 times 2x minus 1, which is basically x minus 1/6. So this linear polynomial is the projection of x square onto the subspace of linear polynomials. Finally, in order to find the distance between these two polynomials, you have to just subtract the two polynomials and then find the norm of that. So that would be simple. This is x square minus 1, x minus 1/6 is the polynomial along. You can think of like the polynomial that goes from this to that polynomial, and you just multiply it by itself and integrate to evaluate the inner product and take square root. So that's about it for these questions. So like in case you have any more questions, you can type them out in the chat box. We'll wait for a few minutes, and if we don't have anything else, we can continue with the additional questions.
Yes, please type in your question to the chat box. We have 40 more minutes left, and we would like to take your questions on the contents of week 5 to 8. Any concepts of week 5 to 8, or any of the questions that were covered in the assignment of week 5 to 8. Yeah, please feel free to ask your questions in the chat window of the.
Yeah, even if something was not clear in like what we explained today or anything, please feel free to put your questions in the chat box. We'll wait for a couple of minutes. Okay, so yeah, do you think we could like go ahead with the least squares thing, or? Okay then. Yeah. So if there aren't any questions yet. There was something that we wanted to discuss, which might be useful to you. So in the question for the least square solutions, we noticed that we had a case where the map itself was invertible, which means that you could directly just invert the map and satisfy an equation as ax equals b. So this is a special case out of more general variety of least square solutions. So I thought I'd probably spend a few minutes and go over the different cases. Now, the case that we saw in the question was the first case where T is invertible, where this is possible only when m equals n. So if you had a matrix, say 2 by 2 matrix, for example, then if you had the xy plane and you had a particular vector w, which is in R2, which is given, and we want to find the TV, that we want to find the V, which maps to this W. And this is directly possible. We want to minimize TV minus W because T is invertible, the range of T is basically the whole XY space, which means you could directly find some V which maps to the vector W. So here it's very simple. You just satisfy TV equals W, and there is only one unique vector V which satisfies TV equals W. Now let's take the second case where T is surjective, but it's not injective. What I mean by that is the range of T is equal to Rn. let's take the simpler case where m equals 2 and n equals 3. So let's take the range of t to be equal to R3, and we have the map going from R2 to R. Sorry, range of t is R2, and the map is going from R3 to R2. So we have a fat matrix over here, and we're going to have 3 vectors over here. So by saying that the map is surjective, we mean that this has a full column rank, in the sense that the column rank is equal to 2, which is the maximum possible. And now, because the column rank is 2, it means that the nullity of the matrix is equal to 1, which means it will be non-injective. Now, if the map is non-injective, so let's see what happens. So let's imagine we have the 3D coordinate space like this, and because this is a 2 by 3 matrix, let's assume we're dealing with standard basis. The range of t is basically the xy plane. So if the range of t is only the xy plane, if we have a vector w, the vector w actually also lies only in the xy plane, because the codomain vector space is also R2. So the range of t, that's basically what I mean by full column rank, where the range is equal to the codomain. So the vector w is always going to lie in the range of t, even though it's just the xy plane, which means tv equal to w is possible. But how do we find the v corresponding to this w? So let's say this is one v which corresponds to this value of w. So let's say there is a vector v which maps from this point in space, which could be anywhere in R3, to the vector w. But we also know that the nullity of this matrix is equal to 1, which is because it's non-injective, it's going to have a non-zero null space. In this case, it's going to have a null space of dimension 1. So that might be a line passing through origin, which represents the null space of the map T. Now, if we have a certain solution V that maps to W, then another line that passes through V, which has vectors added to it along the null T. So this is basically a translate of null T, and where V is the vector which is in that translate. So all of these vectors are going to map to one single vector W, which is going to lie in the range of T, which means it's going to satisfy TV equals W, and it's going to have infinite solutions for that. So this is basic TV equals W equation that we usually solved earlier. Now we have a problem when T is non-surjective. So this is possible only when m is greater than n. So let's say m is equal to 3 and n equals 2. So in this case, the range of let's draw the matrix. This is going to correspond to a tall matrix. By saying that this is injective, I specify that the rank is going to be 2. So if you have two columns in this matrix, so this is 3 cross 2 matrix, then it's going to have 2 linearly independent vectors. This is the case that I'm considering, where T is non-surjective. It's non-surjective because it's impossible for 2 linearly independent vectors to cover the codomain R3. So which means that the range of T is going to be a plane in 3-dimensional space. So this is going to be U, which is range T. And let's say we had some vector W that we would like to minimize TV minus W. This vector can lie on the plane, or it might exist somewhere outside the plane. So let's say this is W1 and this is W2. For W1, TV equal to W can be directly satisfied, and we have the case that we had earlier, which is almost identical to the first case, where we have TV equals W satisfying. And because the map is injective, you have a unique V that maps to this value of W. Now, what if W2 is not in the range of T? In that case, we have to take a projection. So what we did in class was, if we had an equation AX equals B, we pre-multiplied by A transpose, and we set the A transpose times AX minus B equals 0. So what we mean by that is we're trying to project the vector W onto the subspace range T. So this, if this is the projection, then this is the closest distance of W from W2 from this from the range of T. And in this case, because the map is injective, a unique V exists which maps to this value of TV. So this gives you probably a better picture of what least squares looks like in the case where it's not surjective but the map is injective. For the general case, it's I think you would have easily guessed what the general case looks like. Let's take a slightly simpler case where you just have a 2 by 2 matrix, let's say 1, 2, and 3 and 6, and just to keep things simple. So the range of T in this case is going to be the column space. So column space is basically the line through origin, which contains 1, 2, 3, 6 is going to lie somewhere around there. Now, in this case, I've taken an operator which is neither surjective nor injective. So because of that, it's going to have a non-zero null space. And what is the null space of this? It's going to be minus span of minus 3, 1. So it's going to be a subspace which is something like this, which passes through minus 3, 1. Now we have the range of T over here, and we have the null of T over here. Now let's say we had a vector W which lies in this somewhere in this xy plane. If W lied on the range of T, it means that you're going to have a vector V, and you'll be able to find a vector V which maps to this point on the range of T. But let's say this is the vector that maps to W1, but that won't be unique because we have a non-trivial null space, which means all of the vectors along the null space, which is passing through V, are going to map to that W1. If W1 is not W is not on the line, for example, W is over here, then you're going to have to find the projection onto this line, and in turn you're going to have to find the V that maps to this value of TV, and that is not going to be unique. You'll be having a whole translate of null T which maps to that value of TV, and that is going to be the vector which has TV. All of these vectors have TV which maps to a point which is closest to W2 in the range of T. So there's quite a lot of detail in what is going on in least squares. So I hope this gave a better picture of what it means when we say there is a unique minimizer for TV minus W, what it means when we say that the minimum has multiple solutions. So this, I hope this gave a better picture of what it looks like. So yeah, if you had any questions about this, please make sure you put it in the chat box. So if we don't have any more questions, we can like move on to the additional questions, I guess.
Yeah, so in the additional questions, we have 5 to 6 questions again on the contents of week 5 to week 8. The first one is on arithmetic and geometric procedure. So the question says T is a linear map on the vector space. T is a linear operator on the vector space V, and that vector space V has a dimension n. And we are given four options, four statements about the geometric and arithmetic multiplicity of eigenvalues, and we need to figure out which of these are correct. So the first statement says that geometric multiplicity is equal to arithmetic multiplicity for all eigenvalues is possible if only if the operator T has n distinct eigenvalues. The second statement says eigenspace of any eigenvalue will be a subspace of V. The third statement says the intersection of eigenspaces of distinct eigenvalues will contain non-zero vectors. And the last statement says geometric multiplicity is equal to arithmetic multiplicity for all eigenvalues, implies that the operator is diagonalized. And the option, and we also have options which say only if the first three are true, only second and fourth statements are true, only the second statement is true, or all are true. Let us first see if the first statement is true. We know that identity operator, all the eigenvalues of the identity operator are 1. So the eigenvalue 1 has a geometric multiplicity and arithmetic multiplicity both equal to n. But the first statement says geometric multiplicity and arithmetic multiplicity for all eigenvalues is equal only if the operator has n distinct values. But identity operator is a counterexample for this statement because it has only one eigenvalue 1, which has arithmetic and geometric multiplicity equal being n. So if we go to the next statement, an eigenspace of an eigenvalue is a span of the linearly independent eigenvectors corresponding to that particular eigenvalue. So any eigenspace will be a subspace. So the second statement is correct. And so since eigenvectors corresponding to different eigenvalues will be linearly independent, the intersection of eigenspaces corresponding to two different eigenvalues will only have zero vector in common and do not contain any non-zero vectors in common. This is because the eigenvectors corresponding to distinct eigenvalues are linearly independent. So statement 3 is wrong. And the final statement is if arithmetic if the final statement is if arithmetic multiplicity equals geometric multiplicity for all eigenvalues, it implies that the operator is diagonalized. Let us see the reason for this. So since the sum of arithmetic multiplicities of all eigenvalues equals n, and eigenvectors of different eigenvalues are linearly independent, if geometric multiplicity is equal to arithmetic multiplicity for all eigenvalues, then this implies that the operator will have an eigenvector basis. So statement 4 is correct. So statements 2 and 4 are correct and 1 and 3 are wrong. Let us now go to the next question. It deals with eigenvalues and their implications on rank and nullity of the matrix. So we are given an operator T on the vector space R5, and it is represented by matrix M with respect to a standard basis. The solutions of the characteristic equation determinant of M minus lambda equals 0 are 3 zeros, 1 and 5. We are asked to find the sum of maximum possible rank and minimum possible rank of the operator T. So we know that the roots of the characteristic equation determinant of M minus lambda equals 0 are nothing but the eigenvalues of the matrix M or the operator T. So the eigenvalues of the matrix M or the operator T are 3 zeros, 1 and 5. This means that 0 is an eigenvalue of the operator T, and since it is an eigenvalue, there exists at least one non-zero vector such that TV, one non-zero vector V such that TV equals 0 times V, which is 0. So the null space of T is non-trivial. That means the dimension of null space of T is at least 1. And since we know that geometric multiplicity of an eigenvalue is always less than or equal to the arithmetic multiplicity of an eigenvalue, geometric multiplicity of the eigenvalue 0 is less than or equal.
I'm not. I don't think I can hear you. Prafulla.
I think we have some problem with Praful's mic.
Probably some network issue.
Yeah, okay, like, I guess we can, like,
We can go ahead. Others.
yeah, so like
Sorry,
since
I think the connection got lost.
okay.
I don't know, maybe I can again start from the solution of the question.
It got lost only in the last statement, like
Okay. So because 0 is an eigenvalue of the operator T, we are sure that there is a non-zero vector V such that T equals 0. So null space of T has dimension at least 1. But we also know that geometric multiplicity, which is the dimension of eigenspace of an eigenvalue, it is less than or equal to its arithmetic multiplicity. So the dimension of null space should be less than or equals 3. So, which gives us the bound that the dimension of null space of T lies between 1 and 3 for the given example. And so using fundamental theorem of linear algebra, which says that rank of an operator plus nullity equals the dimension of the vector space n, we get nullity lies between 1 and 3 implies that rank of this operator lies between 2 and 4. So the maximum possible rank is 4 and the minimum possible rank is 2. And we are asked for the sum of these two values, which is 6. Yeah, so maybe we can go to the next question. Next question is a short one on outer product. We are given two non-zero column vectors V and U, and the matrix A is defined using them as U times V transpose. So U is a column vector and V is a column vector. So V transpose is a row vector. U times V transpose will be a matrix. It will not be a single value. If it was V transpose U, it would have been a single value. U times V transpose is a matrix. And we are given options and we need to say which of them are true. It's just V is an eigenvector of A, U is an eigenvector of A has rank 1 or none of them. So we see that in U times V transpose, we see that each column of A is a scaled version of U, or each row of A is a scaled version of V. This means that all the columns are A are scaled versions of V, which means the rank of A or the
we lost you again. Okay, so yeah, when we have given that U is the only it's linearly independent vector in the column space, which means that that is if there is an eigenvector for A, it can only belong to the range of A or the column space of A. So the first option, so the second option is a possibility. It might be true. So we'll just check that. So if it has an eigenvector, it must be U. So to check that out, we'll see what happens when we act A onto an eigenvector onto U. AU will be simply UV transpose times U. And if you notice, V transpose U is simply a scalar. So you can put it anywhere you want. And this is simply a scalar multiple times the vector U. Now, because we have AU equal to some scalar multiple times U, we have U to be an eigenvector of A with eigenvalue V transpose U. So if the second option, U is an eigenvector of A, is correct. Now, here we've assumed that V is not a scalar multiple of U. So in this case, we don't consider the case of first one. So I think that was mentioned in the original question. Now, as we mentioned earlier, the column space of A simply consists of the vector U. The span is a vector U, which means it has only one linearly independent vector, which means it has rank 1. So the third option is also true.
Yeah, sorry, my connection got lost again in the middle of the last question. Hope I'm audible now.
Yeah.
Yeah, so yeah, maybe I'll by picking up from this question.
Yeah.
Yeah. We are told that P of X is a degree 2 polynomial, and it is such that integral p square of x from 0 to 1 equals 9. And we are asked the maximum possible value of integral p of x times 1 minus 3 times x square over 0 to 1. So given any two polynomials p of x and p of x in the vector space of polynomials with degree less than or equals to, which is p2 of r, we can define the inner product as integral of p of x times p of x over the set 0 to 1, over the interval 0 to 1. So using this, we are asked the value of integral 0 to 1 p of x 1 minus 3 times x square. So this becomes the inner product of p of x and 1 minus 3 times x square with this definition of inner product. Next. And we are also given that integral 0 to 1 p square of x dx is 9. This means, according to this definition of inner product, this means that the norm of px square is 9. And from Cauchy-Schwarz inequality, we know that dot product, the magnitude of dot product of two vectors is upper bounded by the product of the respective norms. So the magnitude of the inner product of p of x comma 1 minus 3x square, which is nothing but the magnitude of integral 0 to 1 p of x times 1 minus 3x square, is upper bounded by the norms of p of x and 1 minus 3x square with the inner product defined as above. So easily we can calculate the norm of 1 minus 3 times x square to be under root 4 by 5. And substituting the values of norms of p of x and 1 minus 3x square in the Cauchy-Schwarz inequality above, we get the magnitude of the integral to be 6 by under root 5, and the maximum minimum possible values of the integral are 6 by under root 5 and minus 6 by under root 5. Yeah, maybe we can go to the next question. Yeah, the next question is on an interesting concept called Riesz representation. We have said that there exists a polynomial q in the set of all degree 2 polynomials such that for any polynomial p of 1 equals integral over minus 1 to 1 p of x times q of x. If q, so we are asked if q of x has the form ax square plus bx plus c, what is the value of 2 times of a minus b minus c? So let us first define a mapping for every polynomial p in P2 of R such that p of p equals p of 1. The mapping phi maps every polynomial p in P2 of R to p of 1. That is the polynomial p of x evaluated at the value 1. Using the inner product defined as integral over minus 1 to 1 p1 of x times p2 of x, an orthogonal basis for the vector space of all degree 2 polynomials, all polynomials with degree less than or equal to 2, can be obtained as e1 equals 1 by root 2, e2 equals under root 3 by 2x, and e3 equals 3x square minus 1 by 2 times under root 5 by 2. And now we use the Riesz representation theorem, which says that for any linear functional p, there exists a vector v such there exists a vector u such that p of v equals inner product of v comma u, and that u is actually the polynomial q here, which is phi e1 conjugate times e1 plus phi e2 conjugate times e2 plus phi e3 conjugate times e3. We have defined the function phi as a polynomial evaluated at the value 1. So phi of e1 will be 1 by root 2 because the value of e1 at any x is 1 by root 2. Phi of e2 will be under root 3 by 2 because the value of under root 3 by 2 x evaluated at 1 is under root 3 by 2. And similarly, we evaluate e3 at 1 to get p of e3 as 1 times under root 5 by 2. Substituting these values and the expressions for e1, e2, e3, we get the required polynomial x. We get the required polynomial p of x, which satisfies the condition, given condition. Yeah. Yeah, maybe we can go to the next question. Yeah, so this question is on projection operators. So a real matrix M represents a projection operator if and only if M square equals M. It is called, such an operator is called an orthogonal projection operator if and only if M square equals M along with M equals M transpose. If M square equals M but M is not equal to M transpose, such an projection operator is called an oblique projection operator. We are given 4 matrices and we need to check whether each of these are orthogonal projection operators or oblique projection operators, or whether they are projection operators at all or not. Let us go through each option one by one. Next. Yeah, so the first option is the matrix 0, 0, 0, 1. Squaring it, we find that it again has a form 0, 0, 0, 1. So it is a projection operator, and it's also symmetric in that its transpose equals itself. So it is an orthogonal projection operator. The second option is 0, 1 as a first column and 0, 1 as a second column. Squaring it, we again get the same matrix. So it is a projection operator, but its transpose is not equal to itself. So it is an oblique projection operator. The third option is 1, 0, 0 as the first column, 1, 1, 0 in the second column, all zeros in the third column. Squaring it, we get a matrix with 2, 1, 0 in the second column. So M square is not equal to M in this example, so it is not a projection matrix at all. The last option is 1, 0, 0 in the first column, 0, 1, 0 in the second column, all zeros in the third column. Squaring it, we again get the same matrix, and we also see that its transpose is equal to itself. So it is an orthogonal projection. We have one last question left. It is a small, simple question using the properties of eigenvalues and eigenvectors. So we have said that T is a linear operator on a vector space of dimension 2, and we have said that there are two non-zero vectors u, w in V such that T times u equals 4w and T times w equals 4u. We need to find the product of eigenvalues of T. We have said that u and v are neither equal nor are the additive inverses of each other. So we are given tu equals 4w and tw equals 4u. So adding these two equations, we get that t of u plus w equals 4 times u plus w. Since u and w are not additive inverses of each other, u plus w is not 0. It will be a non-zero vector. So 4 is an eigenvalue. Similarly, subtracting the equation tw equals 4u from tu equals 4w, we get that t times u minus w equals minus 4 times u minus w. Since u and w are not equal, we again get that u minus w is a non-zero vector and minus 4 is also an eigenvalue of t. Since the dimension of the vector space is V is 2, 4 and minus 4 are the only eigenvalues of the operator t. So therefore, their product will be minus 60. Hope this was clear. Yeah. If you have any questions, please write them down in the YouTube chat window. We do have 5 more minutes left, and yeah, we'll try to clarify the questions. Thanks.
Yeah. So I guess many of us might be watching the session later on as a recording. So in case you are watching it, please make sure that you do fill in the form at least for the next session, so that like any kind of doubts that you have, even though the exam may be postponed, like this is your opportunity to ask a question. So we'll be available to answer your questions. So please make sure that you try and look at the concepts and look at the questions maybe, and see if anything is unclear to you. And, that'll be great if you could let us know your questions.
Yeah, so the next session will be on the weeks 9 to week 12. So please put in your questions and doubts on weeks 9 to week 12 in the Google form that would have been shared with you. Weeks 9 to week 12 cover the concepts of normal operators, adjoint operators, complex spectral theorem, real spectral theorem, and the concepts of isometries. and the singular value decomposition and polar value decomposition.
So like gradually, like the topics also become a little more dense, and like the kind of properties they do come in very well. They beautifully come together, as well as there is a lot of detail and content that might end up being a little confusing. So so make sure that you don't have any like things that are nagging you that are not extremely clear. Yeah.
Yeah, thanks for joining for the session. Please do join for the next session, and please do fill in the form with your doubts on the concepts of week 9 to week 12. Thanks a lot.
Yeah, even if you have questions on the previous weeks, it's totally fine. We can also cover them, like if you have time. Yeah, so thanks for attending the session, those who joined, and like I hope it was useful for people who are watching it after watching it later. Okay, thanks a lot.